that recording? Yes. Welcome to another exciting biomedical signal processing class. How was your homework? Good? Did you guys come up with interesting and wonderful applications for correlation?
Yes.
Yeah? Mike, what'd you have?
Yeah, so I thought of 4 different things. I don't have it in front of me, but one was like a heart rate monitor that also, in case of a heart attack, similar to Life Alert, except it would send out an automatic message.
Ooh, I like that.
Police. Yeah.
Yeah.
One that's like sun exposure, like a bracelet or a necklace with a UV type sensor that would sort of remind you if you're been out in the sun too long.
Ah, UV sensor.
Mm-hmm.
That's cool.
Another one was male-female arousal rate that would send out sort of a text message to a partner of your choice based on either like heart rate or like other signs that might be
Wow, it's the Arduino Sex Shield.
Yeah.
Whoa, this is better than the Arduino Death Shield.
As well as also I thought maybe like ovulation cycles that would sort of keep track of different biological processes going on in that region.
Wow. Oh, I'm enjoying this idea of the I am ovulating tweet. That's great.
Send out a message to a partner, and my last
to a partner or just blog it, right? Yeah.
And the last one
That's very creative. I had no idea you were so creative. That's great.
Come back to me.
All right.
I think I have 2 others. I just have to remember what they
Brian, you have one?
Well, I just thought of fingerprints. I thought that was a really interesting biological pattern.
It is.
And we could, we understand it well enough now. I think we could. I looked a little research on it too, and it turns out they actually do use fast correlation with fingerprints.
Yeah, they call this biometrics.
Yeah.
And in biometrics, what you do is you use some sort of a signal that's of biological origin. So it could be your face, it could be your fingerprints, it could be your voice print, it could be a retinal scan. There are all these different things that people use. In my computer, I have a built-in fingerprint scanner. I never use it, but I know that it can somehow unlock the computer with the fingerprint. And so with security, people do 2 primary different mechanisms for implementation. Either they base the security on what you know, like a password, or they base the security on what you have, like a fingerprint or a face print or a voice print or a retinal scan. And so these are the things that kind of try to identify who you are. Sometimes people use another what you have thing. They have a token that generates a key that you're supposed to type in, and when you press it, it gives you a new random key. I've seen some bank cards have that. Others give you a token that you have to look up 3 letters when you go on one side, then you flip it over and you look up another 3 letters, and it gives you a challenge question. And so you've got a kind of a code that you must use for decryption. The one-time pad cipher is like that. You have to have the pad for the decoding. And sometimes what people do with these kinds of ciphers is they use a book. They call it the book cipher. And that's a fairly aggressive way to do the decryption. You have a copy of, let's say, a French edition of something exotic, like a Gideon Bible, that rarely would anyone have. And people would say, geez, why does he have that for? And you're like, okay, and you send messages to somebody else who has the same edition, right? Quite rare. Well, but by virtue of having that, you can get the code key, the page number, maybe an encoded version of the date, and so then you look it up and get the first paragraph and type it in, and then you can decrypt. These kinds of ciphers are very challenging to decrypt without the code. The code books for these things, are highly sought after. In I don't know if you guys are followers of James Bond. You ever hear of James Bond? Well, the author of James Bond was Ian Fleming, and he was a naval intelligence officer, a commander during the Second World War, and he knew that in Bletchley Park, where the decrypting cryptographers were, they were having difficulty decrypting the German code, the German cipher. So he created a plan which was adopted by the royalty called Operation Ruthless. And in Operation Ruthless, this is a true story, you get a crew, a bomber crew of British Special Forces led by somebody who's fluent, word perfect fluent in German. Ian Fleming was. And you use this captured German bomber and join the returning bomber squadron. And then, before you get to the coast, you crash into the English Channel next to a fishing boat and radio for help. They pick you up. You kill the crew. You take their code book. You swim out to the waiting submarine. No kidding. They must have loved drama in the British Admiralty. They loved this idea. You go out to the waiting submarine with the code book in your hands, and you bring it back to Bletchley Park. Now, the only reason they didn't go through with this really daring and wonderful plan is because they were able to crack the cipher in time. But they were on their way. They were ready to go. And this is one of those true stories from World War II. So getting those code books for decrypting the ciphers was so important, because without it you couldn't do it. And Arota, you've got something. Your homework result?
Oh, yeah. I was thinking about body temperature.
Okay.
Like, because during the summer, people are prone to like heat stroke.
Mm-hmm.
And aside from the body temperature sensor, which will tell you when you're oversleep, heart sensor will tell you, how your heart is doing at the same time.
Yes.
Because, like I said, you don't want to have a heat stroke during the summer from overheating. So it's like, oh yeah, it's beeping out. Let's calm down.
That's a great idea. You know, what you could do is you could sort of miniaturize it and give it a Bluetooth transmitter, and then it can talk to like your smartphone or whatever it is you carry around.
Yeah, I was actually thinking about a bracelet.
You know, in one science fiction movie I remember called Marooned, I think that's what it was called, they had these on their wrists, and if somebody was having a heart attack, it would beep at you. And people would get shot, and they would start to go into, it would show you your heart had failed. So it was one of those things where we see this. I think the biological sensors that we see for the consumer are really astounding to me. They're all over in Best Buy, and they're transmitting in Bluetooth to smartphones. And I saw one recently. It was just a scale, but it records the data on the smartphone. So every time you step on the scale, it keeps track of your weight and your progress, which is, I think, very good for the Weight Watchers kind of crew. They try to support each other with tweets about how much weight they've lost, and then they get oh, good work, you've lost another ½ pound, excellent, keep off those carbs, stay away from those mashed potatoes, or whatever it is they do over there, keep eating those prunes. So there's a I don't know, a lot of value in these interesting and wonderful, I'll call them Bluetooth enabled apps that go to the smartphone. And I think the smartphone has kind of been the catalyst for all of this, because now you've got the portable display that can do all of these things. Well, I think that's very interesting. Enabling technologies that you have in your toolbox give you the ability to create wealth by creating new gadgets and new technologies that others will want. And we've become, I will call it, very technology hungry. When you create something like a new shield out of a chip that no one has made a shield for before, the Arduino crowd is all over it. If you said to me, well, I've got this great looking DAC or this great looking A to D converter or this terrific looking femto generator, and I'm going to make a shield out of it for the Arduino guys, and we'll just plunk down a solar cell and we'll give you 5 volts until the cows come home, as long as you have enough light that's normally available in a room, the Arduino guys will just glom right onto that, and they'll say, yeah, I want that. Because without it, they won't be able to do certain things, and with it, you might not even need a whole bunch of software. Just make sure you can go into a sleep mode often enough and only wake up occasionally. It's a big deal. Now, I've seen, and this is kind of interesting in terms of the low power push, I've seen an awful lot of people discussing things like the AT. There are variants on Arduino chips, some of which are quite small. They talk about how they can get nano power, right? The small power systems. And when you have those available to you, you can run for a very long time if your capacitor leakage is low, and if your power management is efficient, and that's key. You have to have efficient power management for that. So what I thought I would do now is talk to you a little bit about the fast Fourier transform, what you can do with it in terms of applications. So far we've talked a little bit about fast correlation. We talked about pitch shifting a little, but I don't think I went into very much detail. One of the things I wanted to do was to try and describe for you a way to do frequency equalization. Now, equalizers, I don't know if you're familiar, but equalizers that allow you to take certain bands and emphasize them. And the bands are ranges in frequency. They'll be something like bass or mid-range or treble, and you'll want to turn those things up. Sometimes you'll have what they call a tone control, which is a very broad, coarse way to change the timbre of the general playback of audio. And I've seen a lot of people become very interested in trying to do things like tone control with FFTs. And so I thought, well, that's not so hard. We should be able to do that. So first I wanted to do was try and review a little bit about pitch shifting via the FFT. And so pitch shifting via the FFT is a really trivial kind of thing to do, which has a large impact in the way things sound. And so what does pitch shifting mean? When you have taken an FFT, what you've done is you've assembled a sequence of frequency buckets, the center of which is DC. And when you want to increase in frequency, what you do is you move away from the center. And the more you move away from the center, that is by taking the buckets and shifting them, the higher in frequency you go. The more you move toward the center, the lower in frequency you go. And so moving buckets around, just not changing their values, just moving them from one place to another and then doing an inverse FFT enables you to shift pitch. Stop me if you have questions. So here's a sample which I did this afternoon. I took a simple oscillator tone and I show you the FFT, and let me see if I can get my mouse. Yeah. So in the center you can see the two side bands. In the top you see the shift, which is 0. I'm showing you the power spectral density, and I'm using Doug's algorithm, and I can play it, although not here in the PowerPoints. Over here I do a shift, and now you can see the side bands have shifted, that is, they've spread from center. So I thought what would be fun is if we could try this ourselves using a real live Java program. So here's my little pitch shifter. What I'll do is I'll show you the sine tone. So here's my little sine tone. And what I can do here is I can spread it out, and maybe I can give you a sense of what the frequency is. This is, let's pick round numbers. 1 millisecond per division. Now let's change the alignment and see how many milliseconds we got. So that's a little more than 1. Here's 1, 2 milliseconds, 2 1/4. So 2.25 milliseconds per division. And so now if I go and get my little calculator out, and I write 2.25 and divide it by 1000, I get the actual value in seconds for the duration of the peak-to-peak waveform. So now if I want frequency, I have to go 1 over that, and he's saying it's about 444 Hertz. So I've done a, I'll call it, I don't know, a frequency counter, only I use my oscope for that. So now what I'd like to do is do what they call a pitch shift. So first I'm going to take my power spectral density And then I'm going to scale up my waveform so that you can see what's going on. So here are the two sidebands at 440 Hertz. And now what we'll use is Doug's algorithm. Increase the sidebands a little. And now I'll do a shift. And we can see the sidebands are stretching. So let's do this play before the stretch. Then we'll play after the stretch. And you can hear a shift in pitch and you can see it. So now if I go back to normal, something has happened here. Something complex. And the frequency has certainly changed. This is 100 microseconds per division. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'll call that 1 millisecond. 1 millisecond is 1/1000th of a second, which is probably close to a kilohertz. Right? So 1,000 cycles per second is what we're seeing in here. But something else has happened. Right? As you go across to the I'll call it other phase, this damps out to almost 0, and then we see a shift from one phase to 180 degrees out of phase. That's the reflected part. That's why you see two sidebands. So both sidebands are present, and you can see them. You can see the time, how would I call it? The time domain reflection about the center axis, which exists as a primary result of there being two sidebands, and that you're having manipulations. So now let's do the following. Let's open a real audio file. So I'm going to open an AU file called space music. Now I'm going to show you the power spectral density of the space music, although first I thought maybe I should show you here's the space music in the time domain. It's not particularly remarkable. Here it is in the frequency domain. And you can see there's definitely symmetry about the center. And now what we'll do is we'll play the sound again. There's the frequency domain. Now what I'll do is I'll do a little shift. And you can see it's a very symmetric movement, right, away from center. And it's changed all of the partials simply by moving the buckets. Slick, right? I mean, you don't get to do these effects normally on your stereo. Not normally. On your synthesizer, maybe not. I mean, how many synthesizers actually do pitch shifting in the frequency domain, and how many do it by virtue of ring modulation, which is simply to multiply it by a carrier that you can alter, and then selecting for subbands. So I mean, yes, you can certainly do that with a ring modulator. An analog synthesizer will do that, but an analog synthesizer will not do it in the digital domain like we just did. So that's quite a different thing. In pitch shifting, you can make the sound virtually unrecognizable. If you have the frequency bandwidth, you can transmit that, and then when somebody wants to hear your scrambled signal, they have to have an FFT and decode it in order to shift it back and get to the original signal. So you can encode audio in this way and find it to be, I don't know, perhaps a reasonable way to do frequency domain encoding of voice. So if you take your voice and you completely scramble the frequency buckets, transmit the sound, and then scramble them back on the way back, you've got a way to do decoding, encoding and decoding of voice in the frequency domain. Yes, sir?
So the frequency domain is what we're looking at now, right?
Yep.
Why is it symmetrical?
Well, that's a very good question. We talked a little bit about the buckets, right? They start at 0. They go out to 1/2 of the sample rate, which is 4 kilohertz. Now here they are again starting at 0, now going out 90 degrees opposed in the other direction. So when you take a Fourier transform and you multiply by the complex exponential in the kernel of the integral, what you're really doing is you're multiplying by the real part, which gives you the left, and the imaginary part, that's the cosine, which gives you the right. And you know that the real part is 90 degrees out of phase from the imaginary part. And when you looked at the sine wave after the inverse Fourier transform, what you saw was it damped out to 0 and then started up with another waveform that was 90 degrees out of phase with the original waveform. So you got a reflection about the midpoint on your Fourier transform. Now you could say, well, how come you can't do the whole thing in the real domain? Well, you can. You can take real signals and then you can do a transform and get real results. They call that a discrete cosine transform. Or if you want to have the full-blown phase information encoded in the output without going to the complex domain, you can use what's called the Hartley transform. So discrete Hartley transforms were first devised by Ronald Bracewell in the 60s, and it was, in my view, one of the first patents that was a true software patent. But they didn't call it a software patent because he had a hardware implementation. Software patents are a relatively new thing to be allowed for the patent office. They didn't really officially start with software patents till the 70s. So if you wanted a software patent, you had to build hardware to capture the algorithm. That's key.
Still a law.
Huh?
Still a law.
The software
It's called
algorithms
machine
can...
or transfer. Yeah, it has to either be tied to a machine or completely transfer something, I think.
Yeah, oh, you're talking about the Bilski ruling.
Yeah, exactly.
In the Supreme Court, they had a process patent which was disallowed because it didn't impact the way energy was transformed by a machine. And he had his business process patent, which is interesting, right? Because if you think about the classic example of something that should not have been allowed as a patent, it would be the one-click Amazon patent, which is absolutely not tied to any particular machine or energy transform. So, I mean, it's a little off point. But the question of exactly what the Bilski patent means has been addressed in one of the IACT meetings by a partner of a law firm, John Yankovich, and we have that recorded on video. So if you go to, I can sort of show this to you. If you go to inventus.org, if I can get in, if I can get to Google, go to Inventus. And now past presentations, and now Bilski versus Kapos, 2010, the new Supreme Court ruling. And now you can see the video of John Yankovich talk about what it means to be compliant with the Bilski versus Kapos ruling. And so that video, it's a funny thing, the speaker didn't show up, so he did an off-the-cuff, completely non-prepared presentation of Bilski versus Kapos, and he was great. He's just great at that stuff. So the other thing he's done is he's been very generous with his time. He's been giving pro bono assistance to our senior projects who want to take their devices and turn them into products. So he's the patent guy. So if you want to get a patent on your stuff. assuming you have something of value to patent. That's another issue. That's a whole other question. Hopefully we'll have that. It's not a requirement for getting an A in a senior project.
But it helps.
It really doesn't hurt. It is oftentimes the case that if you want to license something, having a patent is really very good. If, on the other hand, you don't want to license it and you just want to manufacture it yourself, you're almost better off not getting a patent, especially if there's a secret process. That trade secret can be kept indefinitely at no cost. Yes, sir?
What is the ruling on using other people's circuit schematics or ICs?
In general, if you have something in a data book that's been published, unless there's some encumbrance from a license or a copyright, I don't know of anything that would stop you from using, let's say you're using a chip. I think it's called the LTC 3108, and you look at the Linear Technology Corporation application, and they say this is how you use our chip. There's nothing wrong with doing that. They put that there just so that you would use their chips, and so they would not stop you from using their schematic to implement a circuit based on their chip.
What about something that would come from an article, publishing of a recent design or discovery?
I guess my favorite answer to that question is it depends. If the schematic is a circuit that's been patented, then you might be infringing on the patent. So you'd have to be careful about the claims in the patent. And you might be infringing even if you don't have notice of infringement. Now, the law says you have to have proper notice. But what the law does not say is what is proper. An email may or may not be proper. The court has never ruled. Normally what you get is summoned, or served rather. So if you get properly served by a server, or if you get notarized certified mail in the U.S. Post, that could serve as proper notice. So the question of what is proper is another matter. So for the triple damages thing, they require proper notice, but for the mere infringement on a patent, they do not. So now I've got this other thing I'd like to try and examine, and this goes to the question of equalization. And so first question I have is, what is equalization in the Fourier domain? What does equalization mean to you? What does it mean?
Bringing the buckets.
You're doing what now?
Bringing the buckets possibly back to a normal equalized place, or no?
I don't know. Bringing the buckets. You mean moving them around?
Bringing the buckets
Yeah.
back to what would be considered more of a normal wave.
Well, pitch shifting doesn't move buckets. I'm sorry, pitch shifting moves buckets. The equalization does not. Yes.
Equalization kind of transpose some sort of pattern over your frequencies?
Transpose a pattern. That's good. Equalization is got a transfer function that changes the amplitude of the frequencies.
Yeah.
So what you can do is you can depress certain frequencies and you can amplify other frequencies. So if your FFT has been normalized to give you numbers that range from 0 to 1 in both the real and the imaginary domain, then what you would do is you would take groups of buckets in frequency ranges and you would amplify or attenuate those buckets. And so then the question is, how would you input the signal for the amplification or the attenuation? And this is an interesting point, right? Kind of depends on your application. If what you want to do is equalize for a room, the first thing you do is you take an impulse, and that pulse is fired into the room with speakers, and then you use a microphone and you can measure the resonance of the room, the characteristic frequencies that are present in the room that are higher than others, and then you equalize for the room by forming the inverse transfer function of the impulse. that's how you equalize for a room. But if what you want to do is just muck about with the changing of the amplitude at different frequencies, well, you can just get an equalizer and push all the bars around, and that will be like using a filter bank that amplifies and attenuates certain ranges in your filter. If you have what I will call a tone control, right, which is a simple sort of thing, then in general you can enhance the bass or the treble, and usually you just get 1 or 2 bands and that's it. It'll be the high end, the low end, and maybe the mid end. So, you know, if you said to me, but gee, I'm going to take a long FFT and it's got 2048 samples, how are you going to do that, right? What is, you know, should I use 2048 sliders? Oh my goodness, what would that look like? What a mess. I can tell you I don't really know because I have trouble displaying 2048 sliders. I tried. Could I do 8 sliders? That's kind of a lot for equalizer. Sometimes you can buy these things. They call them 12-band equalizers. And what are they really doing? They're taking the audio range, 0 to 20 kilohertz, and they're dividing it up into 12 sort of parts. If you said there was a 10-band equalizer, I'd say it's 2 kilohertz per band, something like that. And then should I do a long time Fourier transform if all I need to do is get 8 samples? Or maybe I could do a short time Fourier transform and just get 8 samples at a time. Maybe it doesn't even have to be fast. And remember, one of the papers that I showed you said if you have a short enough number of samples, fast Fourier transforms are actually slower than discrete Fourier transforms. So if you told me, well, gee, I'm just going to work with 8 sliders, therefore I only need 8 buckets, and I'd say, hey guy, you don't need a fast Fourier transform. You should just do a discrete Fourier transform. You could say, well, I'm in an Arduino and it only runs at 16 megahertz. And I could say, you know what? You still should only use a discrete Fourier transform until you know you need a fast Fourier transform. Why? Well, A, fast Fourier transforms can be slower. B, fast Fourier transforms that we've looked at so far have required radix 2 numbers of samples. So that means truncation, unless you use an exact radix 2 number of sliders, which 8 would be. So you could use, in theory, a radix 2 FFT, because 2 to the 3 is 8, and that's okay, but it still might be slower than a DFT. And according to my benchmarks in Java, it is. And Java is not particularly fast at these things. So I say a DFT is probably good enough if you're just working with sliders. On the other hand, if you're taking the full Fourier transform of a long sample, you could always take the buckets and you could divide them up into 8 groups. And then you could just attenuate the different buckets by different amounts. And that's legit. And then maybe an FFT would be okay to use. So it kind of depends on what you're starting with. If you're starting from scratch and you don't already have a big FFT that you've processed anyway, why bother, you know, taking 2048 sliders and applying it to 2048 samples? That's just silly. So here's what happens with thousands of sliders. I did a little example here where I put in 8 sliders. 8 sliders is a pain. I mean, that's 8. That's not thousands. I got up to like, I don't know, 15 sliders, and I said, what the heck am I doing? Why do I need this? Right, a 15-band equalizer, you could probably buy that actually. I wouldn't be surprised. But it kind of looks awkward, and there's an awful lot of slide pots there, and sure, it's nothing for me to do it in Java. It's just going to take screen real estate, but kind of a pain to, you know, chuck that out. So then I said, you know, 15 sliders is my limit, and I'm not doing any more than that. So I got 2 ways to look at this. Right, this is a design process. Design is an iterative process. It ends when you run out of time. So here I go. I say, geez, my outcome is I either limit the number of bands or I use another technique to draw the slider characteristic function. Now, if you're going to do some kind of drawing where you're, you know, sort of just drawing freehand with the mouse, and you come out with a shape of what it is you want for your spectral response curve, I'm all for that. That might work. But if you said to me, geez, I just need a couple or 4 bands and that's enough, well, okay, then you just need a couple or 4 sliders, and you're done. And that's it. So I said to myself, well, what would that look like? And so I said, well, we're going to need 4 sliders. We need 4 numbers. They range from 0 to 1. I could take an 8 sample DFT, and I could use the 4 sliders on either half. Remember, the DFT is going to give me 4, and then 4 more buckets 90 degrees out of phase, because it's a complex number. Then I got to normalize the DFT because I want a unitary transform. So I want numbers that range from 0 to 1. So that means I take all the samples coming out in the frequency domain and multiply by 1 over 8, the number of samples on my DFT. Then I multiply by my new filter, which is ranging from 0 to 1 on each one of the buckets. I got to do the inverse DFT. I wrote just play the sample, but I said do the inverse DFT first. I guess I left out a step. Yeah, I could put that in. Do the inverse DFT, then play the sample, right? You can't just do that without doing the inverse DFT, and then play the sample. What do you think of that? Does it make sense? So what I did was I said with a DFT, what did I get? I got 4 completely different buckets on the left and 4 similar buckets on the right, and then I'm going to treat each one of those buckets as a little bandpass filter. Right? So it's a filter bank. 4 filters in my bank. And here are the 4 filters. This is what it looks like. And if you look at it now, you say, geez, you know, that's like the whole interface. That's all I needed. And now the only trouble is, now look at those numbers. They're integers. And they're ranging from minus 100 to plus 100. But that's not too bad, right? I can normalize that to range from 0 to 1 pretty easily. How would I do that? Yeah, how would I make it so that it ranges from 0 to 1? I got numbers that goes from minus 100 to plus 100. Divide by 100. Now it goes from minus 1 to plus 1. Add 1. So now it goes from 0 to plus 2. Now divide by 2. Geez, this is a very iterative design process you have here. How about this? How about if we add 100 and then divide by 200? Is that good? That's the same thing, right? Okay. I like that. That's a good one. I like the process you went through just now. That was good. I went through the same process myself. And it's so here it is. You want to map from minus 100 to plus 100 so that it ranges from 0 to 1. You're getting something that goes from minus 100 to plus 100, so you add 100. So now it's going from 0 to 200. You divide by 200, and now you got something that goes from 0 to 1. And then you say, oh, I understand how this works. Let's take the whole thing with these values coming in, and I'll call it scale. So here's an array of values that go from minus 100 to plus 100. They're all integers. I'll convert them into an array of doubles that go from 0 to 1 by doing this little allocation of an array, which could be expensive, really. I mean, I don't know how much that costs. I could probably have reused the double precision array, but so what? You don't change your sliders that often, and they're certainly not being changed inside of the loop where you're going to be doing your signal processing. So it's kind of okay. Maybe not terribly efficient, but efficient enough if you're using a graphic user interface to generate these slider values. And then I go through each one of the values and I do my little scale doodad, and then I return my array of values. What do you think of that? That works, right? So what do we got here? Something here called GUI.run for slider panel, and that gives you 4 sliders. And if you look at this real carefully, you see that's a tab pane right in there. That's kind of a nice thing because it means you can add more tabs for other interfaces. But over in here on the right, that's what they call a spinner. That means you can actually type in values in a valid range from minus 100 to plus 100. And you got over here this little up arrows and down arrows. they allow you to do increments. So in practice, it gives you a nice convenient way to do an interface. So here's my little scale feature, and if you look at how scale is implemented, there it is, add 100, divide by 200. You got this here, run for slider panel. Every time you get a change in a value, it calls run, and then you call get value, and it gives you the 4 values. They're labeled quad. You go to the quad values, you get them as an array of ints, you pass them into your scale, and then you can print them out, do whatever you want. Set them, get them, print them, multiply them. They're there. When you run this thing, you get this lovely little interface, and the slider becomes a controller. And the view of the value of that slider appears on the right. The text field on the right also becomes a controller, because if you change that value, the slider changes in correspondence. And the up arrows and the down arrows also become controllers. So you've got kind of a very consistent view of the number model that's being used to alter the values coming off the bottom. And I don't know if you've noticed it, but in the background you can actually see some values that presumably range from 0 to 1. So here's 0, 0. This is 3/4 of the way. That's over in here. This is 38% of the way. That's over in here. So I can make this 100% of the way, and 3/4 of the way, and then 0 of the way. So that's a 4 numbers, 4 bands, ranging from 0 to 1. So for an equalizer, that's all you really wanted. So what is the center frequency for each one of these bands? Let's assume the sample rate is for, what have we been doing? 8 kilohertz sampled audio, right? That's what they call EULA encoded. So if it's 8 kilohertz sampled audio, what's the maximum frequency? Yeah, 4 kilohertz. So now I got 4 sliders with 4 kilohertz. Each slider controls 1 kilohertz. Thinking. So the center frequency for each slider is like 500 hertz. So 0 to 1,000, 1,000 to 2,000, 2,000 to 3,000, 3,000 to 4,000. Those are the bands that I'm controlling here. I didn't label it that way because I don't know what the frequencies will be. This is just a general 4-value input device. I didn't really know what the application would be when I designed it. But we can use it any way you want. And it's just called the spinner model number panel. Because what else are you going to call it? I mean, you could have labeled it with frequencies, but I still didn't know, right? I don't know what a good interface to my equalizer is supposed to look like. That's practically an open-ended design problem. You know, what do equalizers look like when you're designing graphic user interfaces? Should they look like dials? Should they look like slide pots? I mean, I got dials too, and we could start to play with dials, but all of a sudden this becomes a lecture about graphic user interfaces and not a lecture about signal processing. So I'm not really into that, you know. Although I like graphic user interface, great fun. And I got lots and lots of GUI stuff in here too. So that's fun too. But don't want to get too distracted by all this fun. It is possible to have too much fun. So here's my little range scaling. We saw this already. And here's my little equalization panel. And I've got what's called the command design pattern. Well, we really haven't talked much about design patterns. What's a design pattern? Software design pattern. Anybody ever hear the term before? No? Everybody says no.
I mean, I can deduce what it means from.
Go ahead.
Can you repeat the word again?
What is a software design pattern? Mike's Googling it. I can see him. I can see the wheels are spinning.
A common pattern you see in code that is a function.
Okay, that's good.
Like a common way of doing something.
Yes, common practice. In the world of civil engineering, when you design a bridge, if you say, I'm going to design a trestle bridge, you already have a basic idea of what a trestle bridge looks like. If you say, I'm going to design a suspension bridge, there's designs for that. If you said to me, I'm in the world of antenna design, I'm going to design a Yagi antenna. Well, the Yagi antennas are classically directors, radiators, and driven elements. There may be several driven elements, or there may just be one. But in general, this is one of those things that is required for it to be a Yagi pattern antenna. So with command pattern, what you get is the name of the pattern, command in this case, and its role in your system, which is it's a graphic user interface widget that knows how to run itself. So every single runnable element in my run package knows how to run itself. The run buttons, the run menu items, the run choose boxes, the run check boxes, all the run things know how to run themselves, even the run dials. And when something happens, an action, the callback method is run. And then what you do classically inside of one of my little widgets is you call getValue. And the value, that is the state of the widget, is returned. In my case, it's coming back as a quad because it's a 4 slider panel that says 4 numbers, and they're all integers. Now when I go to get the values from those integers, I can proceed to scale them and print them, or do whatever I like. I could set some global variable that allows me to alter how the equalization is run. So any of those things is legit. Now you could say to me, well geez, I could set those values but then not do the equalization because I've got a run button that says OK or apply. And the apply button does the inverse operation of, let's say, the restore button that goes back to where the way things were. So you could have something that reads in off of the file that you used as the source for your audio, and then that'll just get you back to where you were, and then you can change your equalization and then apply it again. Because you don't want to apply equalization on top of equalization in general. What'll happen there is it'll just keep compounding. So couple of ways to go for your interface and what it will do. But one thing I can tell you is every time you touch a slider, the run method will be invoked. And the question of what you want to do computationally inside that run method is a question that you should consider carefully. Because if you do too much computation in the run method, it will slow down your graphic user interface. So then comes the big question, alright, how will you do the equalization? I like to think of it in a few different steps. Open an audio file, display the audio file, play the file, offer to equalize the file with some sort of graphic user interface, apply the equalization. I like the idea of an apply button. Visualize the play file. Or perhaps visualize and play the file. I don't think that's good. And play the file. How's that? That's better. You guys think you can do that? Well, first of all, how would you open the audio file? File reader. It's an audio file. What's the file reader going to do for you? You got to decode it, right?
I'm sure there's a method.
Well, sure there's a method, yes. What method would you use? It's in a ULOC codec-based file, AU file. Any ideas? No ideas?
I forgot what the one where you record.
Well, you could certainly use the recorder. I mean, it looks like the pitch shifter is already doing some of the work for you.
Yeah,
Check out this pitch shifter. I can open a file.
We can't record onto that, right?
Well, that's all right, isn't it?
Yeah,
I was thinking that maybe there was something other than space music. Here's the techno machine. I don't know what that sounds like. It's nice. Yes, sir.
How would one pitch shift in the other direction to lower?
Oh, well then, once you start doing that, you've got to move these. Yeah, your interface here should probably correspond to one of those sliders that goes to -100. So you know that this spinner number model is going to constrain you from going between outside of the range of min and max. So if you tried to put in a number like -100 and hit enter, it beeps at you and says you can't do it. So it guards the input.
In our frequency domain, would we see them overlapping?
You would probably have to zero out these buckets before you shove the numbers. So you'd be losing some of the lower subbands. That's not a bad problem to have. I mean, you can certainly do that. So the pitch shifter's got a real nice interface. It's looking like it's got a little O-scope. It's got a visualization system, and it's got a control panel on the top. I'm kind of liking this. It's not a bad way to go. There's a panel called the O-scope panel. So now I've got two panels, the run slider panel. I've got the O-scope. I could probably put them together. So here's my flow layout, and I know there's an O-scope panel. So if I said something like c.add new O-scope panel, Alt enter, what's that by me? Does that even work? I don't know. Oh yeah, how about that? So you can take an arbitrary whoops. You take an arbitrary whoops, and there it is. So there's a little O-scope over here, starting off with how much is this? Oh, it's looking like 100 milliseconds of audio, and I got some nice numbers here. I wonder if flow layout is the right way to go. How about if we use a border layout and oh wait, we forgot. I need a panel for controlling all of this, don't I? Right, because putting in the numbers is not enough. I got to take the numbers and I've got to do something with them. So I need a control panel that's going to control the operations involved that take this spinner number panel and apply it somehow to the operation on the right. So I need a button control panel. Button control panel. What if we take this lovely little test and move it somewheres? I could move it to sound, since this is becoming a sound-oriented thing. What would be a good place in the project? I'll move it to sound. Where shall we put it? Just sound, maybe? I feel like it should go somewhere. You guys have any ideas? don't know if it should go in there. How about if we put it into sound dot equalizer? Is that a good place for it? Nothing to show? Cut. I really wanted to put it somewhere. Where shall we put it? Make it public too. You tell me. Sound dot equalizer. Equalizer. He's having trouble with the scale function because I made it private. What if we did the following? What if we make it public, and move it as well? So that should give us a main called test2, and see if that works. I like the idea of putting it in its own little equalizer program because that just seems like a reasonable thing to want to do. So now I've got, I don't know, an opportunity to build an interface. What should that interface look like? You tell me. Should this be a border layout? We can put the border layout in here, add the run slider panel, and then after the add method, say comma border layout dot north. Oh, I think it has to be uppercase. And then when we add the O-scope panel, we'll put it in with border layout center. What do you think of that? So then when I run it, I think the O-scope should be in the center, right? More or less. Filling the screen. That's not bad. So then on the top, I've got a little space here for this panel. I could put in another panel if I want. So I could have my sliders on the left and a button control panel on the right. Or if you want, I could do something with menus. What do you think? Menus? File menu? Beg your pardon?
In order to input an audio thing?
Yeah, I think an open would be a good time, right? So maybe what I'll do is I've got this frame here and it's got a container. I think I can go to maybe what I'll do is I'll make a new menu. I'll get the menu bar off the container. Get J menu bar. I think that's how that works, right? And then well, there's a couple ways. You can actually just set the menu bar if you know what it's going to be. You could say do something like this: cf dot set J menu bar, and then you could get something like MB, where MB is your menu bar, and then you want to make a new run menu bar. Run menu bar MB equals new run menu bar, Alt Enter, and you'll want the swing version, and then you could probably put in a run menu, right? So let's do that. mb.add new run menu, and then what shall we call it? The file menu? Not sure I know what I'm doing, but we can do something like this. How about we do that? We make a file menu. Here. Run menu, file menu, equals new run menu, and we put in quote file. There. Then we'll add the file menu. And now in the file menu, I probably need to do something like open. So I can say fm.add run menu, and then I guess it's a menu item, right? Because that's a terminal, and it'll be quote open, right? Isn't that what people do in the file menu? And then public void will need to run something when it's time to open, and add run. I think I needed a new add run menu. New run menu item. There we go. Quote open. I forgot how to do Java. And now public void run. And now if I put in a semicolon and the run menu, Alt Enter, I am there. Right? So this is an anonymous inner class with a run function that does the open feature. And it allows you to select a file and open it. So what we'll do when we run is we'll have some kind of an invocation that says open file and sets up your data structures. Probably ought to run this and see what it looks like. So I should see a file menu, and there it is. And then there's a little open thing. There's the open menu item. I click on it and nothing happens because hey, nothing happens. But I can check to make sure something works by just calling s out and saying open. So if I go in Equalizer, file run open, prints open. So we can see the run method is connected to the action performed when somebody clicks on the menu item. How's that grab you? You guys with me?
Yeah, I just got something different.
Yeah?
You're doing good.
I'm doing all right? Well, I mean, one of the things I was thinking about was this oscillator down in here. You see this oscillator panel? I was thinking that that's got some data structures in it and that I'm going to need it. So I'm just going to put it in as an auxiliary variable, OP, for oscillator panel, and then I'll make it kind of global to this little exercise that we got here, and I'll call it oscilloscope panel, and I suppose it should be OP equals, and then that'll be of oscilloscope panel type, paste. So then when I want to do stuff with the oscilloscope panel, I should be able to do things like set the data structure. And at this point now, I'm kind of weirded out by the way I made everything static. I don't like just working inside of a static method. That doesn't seem right, doesn't seem object-oriented to me. There's just something inherently wrong with doing that. So what I thought I would do is convert this whole thing so that it is got an equalizer constructor, and then the equalizer constructor well, let's see, what can we do in the equalizer constructor? We'll get all of these interesting and wonderful variables. Probably the constructor goes right up through here. And then the equalizer, what do we call this? This whole thing, whatever that is, that block of code goes in here. So I put it all into the constructor. And now what I'll do is I'll make a new instance of the equalizer. And I'll get rid of that silly static test method. Silly static test method. And I'll call that refactoring. Silly static test method. Or SSTM. Right? Silly static test method. Sorry. Huh. What do you think? Did I go too fast just now? I was refactoring because I didn't like the staticness of what I was doing. It was just looking like a big block of code, and it was just not feeling object-oriented to me. So now I got a constructor that does everything that the silly static test method was doing, with the exception of some of these global variables here. And this whole part, which goes to creating the menu bar, that whole section can be, refactored. So I'll extract it to a method and call it something like build menu bar. So now build menu bar is just part of an invocation inside of the constructor. It makes it look better, right? Now it's clear. It's just a little bit more documenting, somewhat more documenting. And then the rest is to create these this layout. And now I can focus on build menu bar. And maybe we can do a run and see what happens. Ooh, something nasty. I was supposed to say new in here. Oh no, this is in the run slider doodad. We can get rid of that. That's gone now. Now let's see if equalizer will run. That kind of looks like it did before. Here's my file, and it doesn't open, but it doesn't actually do anything. What do you think? Now if I look at this O-scope panel, I can see it's got double data. And I'm going to have to be able to get the double data and open up a file and set the double data on this O-scope panel in order to be able to view it. So here's a way to do that through the constructor. But there's going to be a set double data on the O-scope panel as well. So what I'm thinking is that when we get to this equalizer, if you recall your little outline, I got to open the audio file. That's thing number one. And we got an open menu and we know it works. So you tell me, how am I going to open the audio file?
Well, learn how to call a file.
Do what now?
You learned how to call a specific file last time.
What should I do?
I can't tell you offhand, but we learned how to call the specific file.
Well, there's a ULaw codec. Maybe it's ULaw codec. ULaw codec? Maybe it's ULaw codec. ULaw codec sounds slow. Why is it called slow? ULC. equals new ULaw codec. I'm thinking there's a reason why it's called slow, but I don't know what it is yet. And now ulc dot get. Geez, it's not doing anything. I could have sworn we had a ULaw codec handy, and it wasn't called ULaw codec slow either. Oh, it's in ULaw. It's called ULaw codec. That's what I wanted. I don't know why this slow thing showed up. And I think this is supposed to be capital L, isn't it? Oh, it's lowercase l, and it's not slow. It's just ULaw codec. Alt enter, is it? Yeah. Yeah, I don't want the slow. I don't know why there is a slow. What do you want slow for? I want fast. ulc.get double. So there's your double array. And something about that oscope panel. op.set data. And here comes the double. So let's do ulc get double and throw it into the argument there. And I'm thinking that's a good time, such as it is. That's as good as a good time as you're ever going to get in one pass. So let's just run that and see if it works. So file, open, and what did we want here? Techno machine. Open, and sure enough, there's your Techno machine. But I need a file menu to play it. And the other thing I want in the file is like an exit or quit. So I'd like to add a quit item to the file menu, and I'd also like to play this lovely little audio file. So need a menu item. Time for a menu item. Copy, paste, exit, and for exit there's a system invocation, system.exit of 0. And now if I run it and I go to file, there's an exit, and it's done. Well, let's do another one. How about if we want to play the audio data? So the audio data is in the oscope panel. Can you do a play? No. Can you get the audio? The ULaw has a play function. I stashed. I see. I should have kept my data stashed somewhere. So let's grab the data. I want audio data. So let's take the audio data and store it. Audio data. We'll make a little global variable, and then we'll set the audio data. And so for the purpose of programming and doing signal processing, I think we're going to want a nice global variable with data in it. So let's call double audio data array equal to null, and we'll check it for nullness before we use it. And then it'll be set as a side effect. Where is this oscope panel? Here. You know what I'm thinking? If you have the oscope panel already, then you can go to the oscope panel and just say get audio, get double. How did you get the data to begin with? I could have sworn we got the data. Oh, get data. Oh no, you can set the data, you can't get the data. Shoot. Okay. So then we'll just set it equal to null. That's a limit on the oscope panel. So, play. Law codec dot play. Huh. I guess I'll need a new ULaw codec. I hate to keep creating these things. Maybe there's a better way. ULaw codec. I'll bet you sound utils can play this data. Sound utils dot play. Play sound. Play wave file. Process data. Play clip. I got a lot of playing, but it doesn't look like it's playing the ULaw data. So you're saying ULaw data has to be created, right? ULaw data ULC equals new ULaw codec. Pain in the ass. Sorry. Audio data. There's the double data coming in. ULC dot play, and that'll work. A little inefficient. I don't care. Let's see if all that works. So now file open. Techno machine open. So now it should look like the Techno machine, and it should play like the Techno machine. Good deal. And a good deal more. And now I got an exit. This is beginning to look like a program. And I got an outline here. It says display the file. I got a tick mark on that because I did that. Play the file. Ooh, goody, I'm up to step 3. This is cool. Offer to equalize the file. So now I've got to apply the equalization settings in my little sliders to this audio file that I've got. Now we get to do some signal processing. To which I reply, it's about time. Right? I mean, there was a little too much Java in all of this, but at some level, if you wanted to actually implement a program that could do equalization, you had to get past at least a simple, at least an elementary API. So, what do I do now? Arota, you've been awfully quiet. Well, I got to play. How about if I just do the add run menu item? And now I just do something like equalize. So now I got this audio data, and I can play the audio data. Seems to me like I've got to do something. So this is the part where you equalize the data. So how about this? How about we say double array A equals get equalized data. And we pass the audio data in, but we don't have to because it's global. Then we get the ULaw codec and we play it. We go to the oscilloscope panel and we set the data, and that's it. So all you have to do now is implement this little doodad. Implement this. Now to-dos come out blue and they give you a little blue tag in the lower right corner. So when you do to do in the comments, it's special for IntelliJ, and it shows you that you still have something that you meant to do. Now what I didn't do was implement the method with anything other than a trivial return of existing data. In other words, this doesn't do anything. That's why I put the to do in there, so that you could remember to do it. In theory, this should still work, at least as far as I went. And so if I said equalize, I guess it didn't really do much. Oh, I forgot to open the data. I forgot to get the data. Shoot. Techno machine. And now I want to equalize. That doesn't do much. Then I can exit. So probably this has to be implemented somehow. And there are these values, right? And they come in from my little 4 slider thingy. So the 4 slider parameters, they have to be known to the equalize system. So I guess I better get my slider parameters and put them somewhere. So I'll say double slider. Should we call them slider parameters? That's probably a bad name, huh? How about equalizer profile array equals null. So if this is null, don't do anything. Got to protect yourself from throwing null pointers all the time. So if is null, then just return the original audio data. Else, you can do something. Do something. Don't just sit there. Do something. I actually need that else. It'll just do whatever I want after the if. So assuming the equalizer is not null, now what? Shall we print the equalizer profile? Print utils.println equalizer profile. And then return the audio data, because what the hey? Need a return statement for that. So I still need to finish it, but I got at least a little bit further. So now I've got the equalizer values. And when you look at the equalizer values, you can see they're awfully noisy because there's these print line thingies. But you don't need that. And the equalizer values, they can just be set. Equalizer values. Isn't that what we called it? Oh no, profile. And that's it. So that communicates to the subroutine that does the equalizer values, and then now I got to implement it. Now it's just business logic. It's just business logic. And it shouldn't be noisy anymore when you start to drag these things around, and it's not. The only time it gets a little bit noisy is if you have something to play. What's this? Wave? Space music? Space music. So now if I go and play it, it should play. And if I do equalize, you can actually see the values. So the one thing I didn't do was the signal processing part. Yes, sir.
Should we take a break?
Yes, absolutely. So let's take a break and stop this.